On December 3rd, an enormous antenna hanging down from a flying balloon roaming around the sky 40 kilometers over the Antarctic ice measured an ultra-high energetic radio signal coming from below the Earth's surface. That was not the only event that the neutrino experiment ANITA measured. In almost a single month, around 26 days, it measured 4 radio signals with such overwhelming energy. But how come such an energetic radio wave was emitted from under the ice? The standard explanation is that it came from a very special kind of astroparticles, tau neutrinos. If these neutrinos were sufficiently ultra-high energetic, they could interact enough with the Earth and produce a tau lepton, which would, after some time, decay into an electromagnetic radio signal that the antenna would have measured. However, there is one big problem. If the ANITA antenna saw 4 ultra-high energy signals in 1 month, how come other similar experiments have seen no neutrinos like these ones at such energies yet? For example, the enormous IceCube experiment has not seen any of them in 9 years of measurements. If you assume that the Earth is constantly showered by these neutrinos, it is almost impossible for them to explain both the 4 events at ANITA and the absence of events in IceCube at the same time. So what caused these events? In our work, we proposed that the signal came from beyond the standard model BSM particles. Our goal is to better understand the synergies between ANITA and other experiments like IceCube when trying to unravel BSM scenarios. The process we study is analogous to the standard model. We assume a flux phi of BSM particles that interact with the nucleus with a cross-section sigma and produce a secondary BSM particle which decays after a lifetime tau, producing a shower for the ANITA events. For example, this flux of particles could come from the decay of extremely massive dark matter. First, the ANITA antenna, thanks to its great angular resolution, can already constrain a lot of possibilities. That is, if I have seen the shower coming from slightly below the horizon but not from anywhere else, this already tells me what is the most efficient trajectory, which will depend on how the primary particle interacts and how the secondary decays. Second, that when taking into account the absence of events in IceCube, the possibilities are even more constrained, but it is possible to explain both experiments in this scenario. Luckily, future IceCube data will be able to tell us more. Ultra-high energy neutrino experiments are just beginning, but they have a lot of discovery potential. However, to take the most out of them, we need to understand them better than we do. And an excellent way to do this is through its synergies with other neutrino experiments such as IceCube.